Welcome you all. Today we are going to discuss one more exercise in turbocharging. A compressor with the performance characteristic shown in figure is operating with a mass flow rate of 49.5 gram per second at an isentropic efficiency of 60%. The compressor is fitted to a turbocharged and intercooled diesel engine. Assuming P, the compressor inlet pressure is 95 kilonewton per meter square. E, the inlet temperature is 291 Kelvin. Gamma, the ratio of gas specific heat capacities is 1.4. Cp is equal to 1.01 kilojoule per kg Kelvin. Calculate the pressure ratio, the compressor speed, the compressor delivery temperature, and the compressor power. If the intercooler is removed and the air-fuel ratio is kept constant, how would the compressor operating point is affected? Neglecting any change in the compressor efficiency and pressure ratio, estimate the maximum increase in output that the intercooler could lead to. State clearly any assumption that you make. So the given data is compressor, the performance characteristic is given. The method is the turbocharged and the intercooled diesel engine. And for the compressor, the mass flow rate 49.5 gram per second, isentropic efficiency 60%, the inlet pressure 95 kilonewton per meter square, inlet temperature 291 Kelvin, the ratio of specific heat, that is gamma, of gases is equal to 1.4, Cp of the gases is equal to 1.01 kilojoule per kg Kelvin. Calculate the pressure ratio, the compressor speed, the compressor delivery temperature, and the compressor power. And if the intercooler is removed and the air-fuel ratio is kept constant, how would the compressor operating point is affected? Neglecting any change in the compressor efficiency and pressure ratio, estimate the maximum increase in the output that the intercooler could lead to. State clearly assumption that you make. So, they given a compressor performance characteristic map, the mass flow rate M and the inlet pressure and the inlet temperature to the compressor. Then they given isentropic efficiency of the compressor and gamma value, Cp value. Now they are asking A, pressure ratio, B, compressor speed, C, delivery temperature, D, compressor power in 1. Then so we know that the pressure ratio is equal to P2 by P1 for a compressor. Second, the compressor speed, that is N of the compressor. Then compressor delivery temperature, that is T2 dash. Then compressor power, that is work of compressor, they are asking. So what is the input value is, the given mass flow rate is equal to 49.5 gram per second. We have to find out this mass flow parameter is equal to m into root of T by P, where T is in Kelvin and P is in kilonewton per meter square. Then this mass flow parameter is equal to 49.5 multiplied by root of 291 divided by 95. We will get 8.89 mass flow parameter. Now the compressor efficiency they given it is 0.6, that is 60%. So this mass flow parameter 8.89 and the compressor efficiency 60%, we will get the pressure ratio PR is equal to 2.2. So the pressure ratio is equal to P2 by P1 is equal to 2.2. Answer 1. Now the question number B of 1 is compressor speed. We know that the speed parameter, from this we can find that N by root of T is equal to 4690. Then N of C is equal to root of T into 4690. That is equal to root of 291 into 4690. That is equal to 80,005.4 RPM. Answer 1B. Now the 1C is delivery temperature of compressor. That is for isentropic compression from state point 1 to 2. We know that T2 by T1 is equal to P2 by P1 whole to the power gamma minus 1 by gamma. T2 is equal to T1 into P2 by P1 whole to the power gamma minus 1 that is equal to 291 into 2.2 all to the power 0.4 divided by 1.4, we get 364.525 Kelvin. However, the actual compression is deviated from the ideal compression, that is 2 dash. Now, we know that isentropic efficiency is equal to ideal compression over actual compression, that is equal to T2 minus T1 over T2 dash minus T1, that is 0.6 is equal to 364.525 minus 291 over T2 dash minus 291. We get T2 dash is equal to 413.54 Kelvin, answer 1C. Now the next question is compressor power, that is work of compressor is equal to mass of air multiplied by Cp of air into T2 dash minus T1, that is equal to 49.5 gram per second, that is 1000 kg per second. Cp 1.01, T2 dash 413.54 minus 291, we get 6.126 kilowatt. The second question is, if the intercooler is removed, means what will happen to the compressor parameter? First, if the intercooler is removed, means the temperature of air increased, so that the mass flow to the engine is reduced, so that the mass flow parameter is reduced. Second one is, if high inlet temperature to the engine, then higher combustion chamber temperature, so that the temperature throughout the cycle is increased, turbine inlet temperature is increased, so that higher power is transmitted from turbine to compressor, so that pressure ratio is increased. So in this case, so when the intercooler is removed, means mass flow parameter is reduced, pressure ratio is increased, then compressor speed parameter is increased. Now the assumptions are, one is perfect intercooling, then second one is the mechanical losses from turbine to compressor is negligible, then third one is specific heat capacities and gamma values are constant, it is not vary with the temperature. Then the third question is, assuming all parameters are constant, then increasing of the power output with the intercooler. So assume that the inlet with perfect intercooling, the inlet temperature to the engine is equal to 291 Kelvin. However, without intercooling, the inlet temperature to the engine is equal to 413.54 Kelvin. So all the parameters are kept constant. The engine power is directly related to the mass flow rate, so that the increasing of the power output is equal to 413.54 minus 291 divided by 291, that is equal to 42.11%, answer 3.
Subscribe to our channel, like if you're satisfied, and share because it may useful to someone.